Hi, I'm Scott Knockby. In this video, we're going to look at the inverse force solution for planar manipulators. So by the end of this video, you should be able to solve the inverse force problems for planar manipulators. So we're going to use the 3R manipulator planar robot as our example. So in the inverse force solution, we'd have a wrench being applied by our robot. Okay, and this would be comprised of both a force and a moment. And we want to find out what are the torques required at each joint. So we want to figure out tau 1, tau 2, and tau 3. So to summarize, we'd be given the wrench that the robot's applying. So this would be Fx, Fy, and our moment Z. And what we're trying to find, what are the required joint torques? Which are tau. In this case, we have tau 1, tau 2, and tau 3. So let's just first look at link 3. So let's consider link 3. So we have our link, and let's say we were to just pin that link. So we're going to have our force acting. So we're going to have a component in the y direction, Fy. We're going to have a component in the x direction, which is Fx. We're going to have our moment about the z, which is Mz. The link length is L3. And what we're trying to figure out is, what is tau 3? So we're going to do the sum of the moments to figure out what tau 3 is. So tau 3 is going to equal this force here, all right, times this moment arm here. So let's draw that in. All right, so this length we'll call Ry, which in this case is equal to L3 S123. So in our sum of our torques here, we're going to have minus Fx times L3 S123. Now we need Fy times this moment arm, so that distance is going to be Rx, and it's going to equal to L3 C123. And so in this case, it's going to be plus Fy, because it's in the opposite direction of the moment's in the opposite direction of the Fx moment. And that's going to be times L3 C123. And then we're going to have our moment Z plus Mz. So that is the torque required by joint 3 to apply that wrench at the end effector. Now we can do something similar for links 2 and link 1. So we just work our way down. So for link 2, we're going to have minus Fx. And now our moment arm in this case is going to be L2 S12 plus L3 S123. All right, so this whole thing you can think of as the moment arm, Ry. It's going to be plus Fy times L2C12 plus L3C123. And this is our moment arm Rx. And we're also going to still have MZ. And then tau 1 is going to be minus Fx times the moment arm. In this case, it's L1 S1 plus L2 S12 plus L3 S123 plus Fy L1 C1 L2 C12 plus L3 C123, and again plus MZ. And that is our inverse force solution. So that is one way we could solve it. But we can also look at it from a power level. So there has to be an equal amount of power going into the arm as there is coming out. All right. So there must be an equal rate of work, which is power, at the end effector level and the joint level. Okay. So at the joint level, our power would be our joint torques times our joint rates, Q dot. All right, and then at the end effector level, it'll be our wrench, which will be F, times our velocity, which is X dot, or V. We sometimes use both. All right, we can say that's the same as F transpose V here. Well, we saw from our forward velocity problem that V is equal to J, our Jacobian, times Q dot. So we can substitute V into that equation above. So we get tau transpose times Q dot on the left is equal to F transpose times J, our Jacobian, times Q dot. So we have a Q dot on each side, all right, and we know that this expression is true for all Q dot. So we can cancel out the Q's. So we are left with tau transpose is equal to F transpose, J. Okay. Let's transpose both sides. So transposing. And we're left with tau is equal to J transpose F. All right, and this is our inverse force solution. Okay, and you'll see that this is the same Jacobian that we had for our forward velocity problem. So you can see there's a duality between the static inverse force solution and the forward velocity problem. All right, we use the same Jacobian, except in this case it's just transposed. All right, but basically once you have the Jacobian from the forward velocity problem, you can easily use it to solve the inverse force solution.